Today's lesson is on section 3.4, day 2, and it is determining other instantaneous rates of change. So we're going to find some other application examples, and in fact we're going to do 3 of them. One is a tank draining, one is a vertical motion problem, and one is an economics problem with cost and revenue. So the number of gallons in a tank, this is about the tank that's draining, by the way. The number of gallons of water in a tank T minutes after the tank has started to drain is given by this Q function. All right, and we have a couple of questions. So this is the number of gallons. This is like our position function. It's actually a quantity function. So we want to know how fast the water's running out at the end of 10 minutes. So in order to get the rate from a quantity, we're going to take the derivatives. So we're going to take Q prime at some time t, and actually we'll evaluate it at 10, but let's just do the derivative first. And we don't really know how to do derivatives like Q, so we need to change this equation into polynomial types in standard form so that we can take the derivative using the power rule. Those equal signs just won't go straight for me. There we go. All right, so we have 100 times 15 minus t times 15 minus t. So if we multiply this all out, we will get a Q function of 22,500 minus 3,000 t plus 100 t squared. All right, so that's the function we're going to take the derivative of. The derivative of 22,500 is 0. The derivative of the next term is negative 3,000, and the derivative of the final term is 200 t. So we want to know what this value is at 10. So we plug in 10 into that equation. We get negative 3,000 plus 2,000, so we end up with a negative 1,000. This is in gallons per minute, and because it's draining, it is a negative quantity, so that's okay. The second question asks what's the average rate at which the water flows during the first 10 minutes. So we're going from 0 minutes to 10 minutes. So we're going to use our average equation, which is Q at 10 minus Q at 0, divided by 10 minus 0. So that's gallons per minute. All right? Okay, the quantity at 10 is 100 times 15 minus 10 squared. And then we're going to subtract 100 times 15 minus 0 squared. All right, so if we calculate that, then we end up with negative 2,000 gallons per minute. All right, and this is an exercise really to show you the difference of an average rate, which is part B, and an instantaneous rate. They're at the same time period at 10, but you can see that the average is negative 2,000 draining per minute, and that the instantaneous at that instant at 10 times, when t is 10 minutes, it's equal to negative 1,000. So there's definitely a difference there. All right, our next example is about vertical motion. All right, we're going to have a dynamite blast that propels a heavy rock straight up with a launch velocity of 192 feet per second. It reaches a height of, and they give an S function after t seconds. So we have feet per second, that's what we're doing. We want to know how high the rock goes. So when a rock is thrown up, it goes up with this launch velocity of 192. It slows down, it gets to a peak, and then it comes back down. And for that one instant that it's at a peak, the velocity equals 0. All right, so what we want to do is find how high it is when the velocity equals 0. So let's look at when the velocity does equal 0. So first let's find the velocity, which is the derivative of the position function, or the height function. It's 192 minus 32 t's. We want to put a 0 in for this and find out when, remember, we just took the derivative of the height position, the height function. Okay, so we set this equal to 0, and we calculate the time. Time equals, I think it's 6 seconds. You calculate that out, but that's not really what they ask us. They ask us how high. All right, the s function gives us the position. So actually, we're going to calculate s at 6 seconds because that's when it was at the highest point. So s equals 192 times 6 minus 16 times 6 squared. And if you calculate that out, you get that the height is 576 feet. All right, so that's your answer to part A, 576 feet. You actually need to do 2 steps. Find the time, then find the height. Now, the next question is, when the rock is 512 feet above the ground, what's its velocity and speed? So right here is 512. And notice it hits 512 once on the way up and once on the way down. So let's find out at what time the position equals 512. So we're going to set the position function equal to 512. All right, that is our original function, 192t minus 16t squared. I'm going to write this again. Unfortunately, this board, even when you're videotaping, doesn't work perfectly. Oh. Okay, you guys get the idea. Set that equal to 512. And you can actually use your calculator to calculate t if you want to. And you should come up with 2 options for that. First of all, let's set this side equal to 0 by subtracting 512. We get 0 equals 192t minus 16t's minus 512. If you want to, this is actually factorable. But if you put it in your calculator, you will find out that your 2 zeros are t equals 4 and t equals 8. If you do not know how to find zeros on the calculator, you need to see me or a classmate and figure that out, because that is one thing you can do on the AP exam, is find zeros with your calculator. So you find the 2 zeros. So actually it's t equals 4 seconds that we're looking for, because that's on the way up. And we want to know the velocity and speed. So we're going to use our velocity equation. Remember, velocity equals, from the part before, 192 minus 32t. So if we find the velocity at 4, we find out that, plug a 4 into the velocity, we find out that it's 64 feet per second. And that velocity is also the speed, because remember, speed equals the absolute value of velocity. So that also equals 64 feet per second. It's just the positive. All right, our next question says, what is acceleration? Remember that acceleration equals the derivative of velocity. So our velocity function is up here. Take the derivative of that. You get 0 for 192, and you get negative 32, and no t. So this is a constant acceleration. It is a constant. And this would be measured in feet per second squared, just so you know. All right, when does the rock hit the ground? Now we know that when a rock hits the ground, its position equals 0. So let's set the position equal to 0. That was our original function, and find out what time it hits. 192t minus 16t squared. Oh. And so we set that equal to 0. Now, the way you can figure this out is by factoring. You could also put this in your calculator, but let's factor out a t. It's pretty easy to do by hand. And you factor out a t and you get these two factors. T equals 0. That makes sense. It starts on the ground. And then we set 192 minus 16t is equals 0. And the time that hits the ground and is at 0 position is 12 seconds. Okay? This is a very important problem. Please study this. There's another example in your book. Please read this section of your book and make sure you understand how to do this. The last application is marginal cost and revenue. This is an economics problem. These are a lot of the variables we're using for cost. We have C of X for cost. X is our number of units. The marginal cost is the cost to produce one additional unit, and that is obtained by taking the derivative of cost. All right, so these are a function and a derivative. Revenue and marginal revenue have the same relationship. The revenue that you bring in can be measured for a number of units, and then you can also measure the revenue of each additional unit by taking the derivative. Notice the average cost equation, which is just like our other average equations. Let's do an example. We're given a cost of some C function, which is given here, and it costs that many dollars to produce X number of radiators when 7 to 9 radiators are produced. The dollar revenue is given by the R equation, and that's from selling X radiators. The shop produces 9 per day. So we're going to find the marginal cost of producing 9, the marginal revenue of producing 9, and then the average cost and the cost of the 10th machine. So marginal cost is the derivative of the cost. 3x squared minus 16x's plus 20. And what we do with that equation is plug in 9 so that we get the marginal cost at 9. So the derivative at 9 equals, make sure you plug in the values. This should be an x. And plug in the values, and you get a marginal cost of $119 per unit. Check my math on that. Marginal revenue. I'm going to write the derivative over here since my board is acting up. It's 3x squared minus 12x's plus 15. Again, we're going to plug in a 9 to get the marginal revenue of the 9th unit. And when we plug that in, we get $150 per unit. Okay, so let's find the average cost of this. Remember, average cost, the equation was on the last slide, but the cost average is the C at 9 minus the C at 0 over 9 minus 0. And if we plug in 9 into our original equation, we should get 261. If you plug in a 0, you get 0, and you divide by 9. So your average cost is $29 per unit. Okay. Last but not least, find the actual cost of the 10th machine. This is actually easier than it looks because you take the cost of the 10th minus the cost of the first 9. Because this is the cost of how many it costs to make 10. This is how much it costs to make 9. So if you subtract them, you get your answer. And this is 400 minus 261. I need 261 because we did it before. And that equals $139 for the 10th machine. And that's the end of our lesson today, section 3.4, day 2.